Seventh graders, believe it or not, we are already at the end of Chapter 7. We are in Section 7.6, which covers systems of linear inequalities. So in the first section, we're going to solve systems of linear inequalities by graphing. So two or more linear inequalities together form a system of linear inequalities. The system below describes the lavender shaded region of the graph. Notice that there are two boundary lines, the red line and the dotted blue line. So here we go. If I graphed x is greater than or equal to 3, remember once again you graph the boundary line and you graph the boundary line. Why is the red line solid? Because anything that you would plug in on that line would be a solution. The blue line is dotted because anything you'd plug in for y would be not a solution. So it says greater than 3, so I shaded the right of 3. Less than -2, I shade below. The lavender shaded region, which is this region, right here. That region represents the overlapping shaded regions, which is your answer. You can describe all of the points of a quadrant with a system of linear inequalities. This region up here, x and y are both greater than 0. In this purpley region, gray region, x is less than 0, but y is bigger than 0. In the orangey yellow region, x and y are both less than 0. And in the green region, x is greater than 0 and y is less than 0. A solution of a system of linear inequalities makes each inequality in the system true. So, the graph, though, is the answer. You can't give me all the answers. So the graph of a system shows all of its solutions. So your answer, most of the time, is just going to be a graph. Example number 1, solved by graphing. Y is greater than 2x minus 5, and 3x plus 4y is less than 12. So let's start graphing these. Now personally, I like solving them, like for example, this first one, it's already solved for y. So I would just graph the equation, which is called the boundary line. Y equals 2x minus 5. So we graph that, which is a review. So I'm going to do 1, 2, 3, 4, -5, up 2 over 1, up 2 over 1, up 2 over 1. Since it's greater than, it's not equal to, so we have a dotted line. And since it's solved for y and it says greater than, I could shade above. Now, I personally don't like that because I always would pick 0, 0 if it's not a line. If I did pick 0, 0, I would get this. 0 is greater than 5, which is true. So 0, 0 side is what's true. Now I graph the second one. Since the second one is in standard form, I'm going to solve using intercepts. The x-intercept is 4, and the y-intercept is 3, 2, 3. And I ran out of room here. It's a dotted line as well. Now let's say you did draw a graph and you ran out of room. I could have solved that for y. (4x equals -3x plus 12). Y equals -3/4 x plus 3. And if you would have graphed that, you would have graphed a point up here at 3 on the y-intercept down 1, 2, 3 over 1, 2, 3, 4. So either way, you would have gotten the right answer. I just ran out of room in my graph. Now, on this one, if we pick 0, 0, we get 0 is less than 12, which is true. So we shade underneath. So where is the region that overlaps? The region that overlaps, which I'm going to put in purple. So let's do purple. All right, purple. Here we go. So the region that overlaps would be this region here, and it would not include the boundary lines because the lines are dotted. So the purple region here would be my answer. Now, you can combine your knowledge of linear equations with your knowledge of inequalities to describe a graph using system of inequalities. So, example 2. Now, example 2. Write a system of linear inequalities from each shaded region below. So, the blue line. I'm going to write that here. The blue, whoa, I forgot to change my font size. All right, so the blue line, I'm just looking at it and I'm going to write it as an equal sign first. That's what I always do. So equal sign. So I'm looking at that and I see, okay, it crosses, oh, it looks like at 3. So that means my y-intercept is plus 3. And it looks like it goes down 1, 2, down 1 over 1, 2, 3, down 1 over 1, 2, 3, down 1 over 1, 2, 3. So it looks like down 1 over 3 gives me a slope of y equals negative 1/3 x plus 3. Now, since we shaded below and it's solid, below is less than or equal to negative 1/3 x plus 3. Now the red, y equals, it looks like it crosses at negative 2. So my y-intercept is negative 2. And it looks like it goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Up 1 over 1 is a slope of just 1, so I get y equals x minus 2. But now it's above, so it's going to be greater than. And since it's dotted, it's not equal to. So y is greater than x minus 2. So the system for this example is the inequalities y is greater than x minus 2 and y is less than or equal to negative 1/3 x plus 3. I want you to pause the video and try this one on your own. So if you did this correctly, this line would just be x equals negative 3. And so that would be, it looks like it's shaded to the right, so x is greater than negative 3. And the blue line looks like it goes through 0, 0. And actually, it's kind of hard to see. Looks like it goes down 2. It goes down 1 over 2. Down 1 over 2. That's hard to see. That'd be a bad example. But down 1 over 2 would be negative 1/2 x. And it crosses at 0. And since it's less than, shaded underneath, and it's equal to, it'd be y is less than or equal to negative 1/2 x. So part 2 is writing and using systems of linear equations to solve real-world problems. I know you're also excited to do real-world examples. So let's start with our first example. Now, in example 3, you can model real-world situations by graphing linear inequalities. When you graph real-world situations, though, you often need to plan how you will scale each axis. Use the values for the x and y intercepts to determine your scale. So example 3. A zookeeper wants to fence a rectangular habitat for goats. The length of the habitat should be at least 80 feet, and the distance around it should be no more than 310 feet. What are the possible dimensions of the habitat? So the first thing I'm going to do is I'm just going to let W be width, since we're talking about length and width. So I'm going to let L be length. So our first equation, the length of the habitat must be at least 80 feet. That's easy. The length of the habitat must be at least 80. So that means greater than or equal to 80. Then it says the distance around should be no more than 310. Well, since we're talking about a rectangle, we have 2 lengths plus 2 widths, and it can be no more than 310. So it could be equal to 310 or less. So we have to graph both of these. Now, obviously your length has to be 80, but I don't think you'd probably want to graph 1, 2, 3, 4 all the way to 80. So I'm going to put length and width as my labels. We're talking about feet, and we love to label. Since my length goes to 80, I'm just going to count by 20s. 20, 40, 60, 80. Since I'm going to use intercepts for my other axis, my width intercept is going to be 310 divided by 2. That's going to be 155. So I'm going to, I'll count by 20s. You know what? No, I'm not. I'm going to count by 30s. So if I graph this, L is greater than or equal to 80. So that means solid line. Greater than would be that way. And my y-intercepts would both be 155. I just realized I'm out of room here. So 120. Well, it's going to be way off the chart here. So 155. It's going to look like that. And since we're doing less than, it'd be underneath. So the shaded region that it could be is anything here plus the boundary regions because they're solid. Now I'm actually going to import something in here, which is a graph that's already done, which is a much better graph than I did. But I want to show you what I did, or what they did versus what I did. Notice that their length and width are switched. So their graph is like reversed. That's okay. So you can actually use this graph as well. So either one, length and width, doesn't matter. So this one they did L is 80 and a shade above. And then they did 155 here, 155 here. And then they connected them, shaded underneath. So your solution is just this shaded region right here. So you could like darken it in if you wanted to, but that's your answer. Some real-world situations have a domain and range that include only integers. In such cases, the solutions will be some, but not all of the points in the region included in the graphs of both inequalities. So, example 4, this is our last one. Suppose you need $2.40 in postage to mail a package to a friend. You have 9 stamps, some are 20 cents, some are 34 cents. How many of each do you need to mail the package? Well, the first thing I'm going to do is let X and Y be something. So I'm going to let X be the number of 20-cent stamps, and I'm going to let Y be the number of 34-cent stamps. So my equations, I have 9 stamps total. First equation would be X plus Y is 9. Now, do you have to use all 9? No. So less than or equal to 9 stamps. Suppose you had $2.40. Well, that means I had 20 cents times X plus 34 cents times Y. I need $2.40. So I have to have $2.40. So that means I have to go greater than or equal to $2.40. Now, if you graph these, I'm actually going to cheat and have a graph already done for you. It looks something like this. I would just graph using intercepts here. X and Y are both 9, so I put a dot right here on 9 and 9. 9 and 9, so the red line represents this one. Solid line because it can be equal to, and I have to have less, so I'm going to shade everything below. I'd also graph this using intercepts. So $2.40 divided by 20 would give me 12. So my x-axis would have an intercept of 12, and my y-axis would have an intercept of approximately 7. Right there. So since that's going to be greater than, I'm going to shade above. So this region right here, this lavender region, is my answer. However, when you would explain this, you would say that the solutions are all of the coordinates that are non-negative integers lying in the region shaded lavender and its boundary lines. You could also say just whole numbers, because if we're talking about how many stamps, you can't rip a stamp in half. So you only can have whole numbers that are represented by the lavender shaded region.